Let's look at this problem. Given an input string S and a pattern P, implement regular expression matching with support for dot and asterisk, where the dot matches any single character and the asterisk matches 0 or more of the preceding elements. The matching should cover the entire input string, not partial. For reference, a regular expression is a sequence of characters that specifies a match pattern in text. Imagine you have two strings. Let's call them word and pattern. The goal is to check if the word matches the pattern according to some special rules. In our special rules, there are two special characters, the dot, which can represent any single letter, and the asterisk, which can represent 0 or more occurrences of the preceding letter. For example, let's say the word is cat, and the pattern is c.t. In this case, the dot and the pattern can match any letter, so the word cat matches the pattern c.t. Now let's take another example. If there is a word cat, and the pattern is cat with an asterisk, this means that the preceding letter, which is A in this case, can occur 0 or more times, so the word cat matches the pattern cat with an asterisk. That's a regular expression. The best approach to solve these types of problems is dynamic programming tables. Do not use recursion, as it is too slow and takes up too much memory. Dynamic programming algorithms are a class of optimization algorithms that solve complex problems by breaking them down into smaller overlapping subproblems and solving each subproblem only once. Dynamic programming tables are just a tabular representation of these algorithms. The key idea behind dynamic programming tables is that if we can solve smaller subproblems and store their solutions in the table, we can avoid redundant computations. By referencing the pre-computed values in the table, we can quickly retrieve solutions for larger subproblems. Here are the use cases. Their versatility and adaptability makes them a powerful tool for many different applications. Let's look at the code to solve this problem. First, we're going to grab the lengths of the pattern and the string and set them to m and n. We add the +1 to include the base case. Next, we create a 2D table with m+1 rows and n+1 columns with all the values set initially to false. Next, we set the base case, an empty pattern that matches an empty string. Next, we handle the case where the string S is empty, has no characters, but the pattern P has an asterisk. Next, we'll create the DP table. First, we're going to iterate through row I from 1 to m and iterate through column J from 1 to n. The next part, we're going to check if the letters are the same or if they're a dot. Then we're going to check to see if the pattern is an asterisk. Finally, we're going to check for multiple characters in a row or a dot, and we're going to return the result. This might not make sense, but let's consider an example and review some of the iterations in the table. Here's the initial table. This is true because of the base case. This is true because of the asterisk condition we set for empty strings. Same here. This is true because the letters are the same. Here we have another asterisk. This table will keep on updating each value in the table until the end is reached. At that point, the final value in the table will be the output. In our case, after examining all the characters in the pattern and the input string, you can see that the entire input string is covered by the pattern, and all the characters match accordingly. Remember to take into account that the asterisk can match 0 or more of the preceding elements. That is a dynamically programmed table. They can get infinitely more complex, but that's the key idea. Check out my GitHub for more problems.